Uh, may I start sharing already just so I can get technical stuff out of the way? Can anyone hear me?
Yes, I can hear you, no problem.
Okay, great. Okay, let me just, because everything usually gives us technical problems, so let me try and get everything ready before we start. Just okay. Okay, hopefully I'm sharing the correct screen there.
Yes.
Okay. Should I just start or?
So, who is chairing the session?
I'm not sure myself.
Okay, I guess you can start because it's 3 minutes.
Sure, okay. So, okay, well, let's start then. If anyone is late, well, I'm very sorry. But as you say, we should start, at least try to start on time. Well, so, I'm Bernardo, and I'm going to talk to you about representations of two-dimensional compatible algebras. This is basically what I've been doing lately for my PhD, which, fingers crossed, should be done by this year. So hopefully this is, I don't know, the culmination of my PhD. And as I'm a PhD student, this is naturally joint work with my advisors, Xabi, Manolo, and someone. So I should start by just very quickly mention what I mean by Lie algebras before I get into compatible Lie algebras and representations and so on. Because for me, as I assume most of us here are algebraists, well, a Lie algebra is an algebraic structure. For me personally, it's not that I don't like the geometry or that I don't care, but I'm most interested in studying things from a purely algebraic point. So for me, and this is so I can tell you what compatible algebras are later. For me, Lie algebra is a vector space with a Lie bracket. Well, this Lie bracket is a Lie bracket because it satisfies these properties of bilinearity, antisymmetry, and the Jacobi identity. And again, for me, these are basically identities. So they have meaning. For instance, the Jacobi identity, if you use antisymmetry as well, expresses that the product is a derivation over itself, but I'm focusing on it as an identity, okay? And then the second ingredient that I will need is the notion of representation, which for me is a way to see a Lie algebra inside a Lie algebra that we already know. So the endomorphisms of a vector space have a natural Lie algebra structure using the commutator of endomorphism, and a representation of a Lie algebra is nothing more than a homomorphism between our Lie algebra and this concrete Lie algebra of matrices, for instance, or endomorphisms. So what this means is that when you apply this map to a bracket, you could just instead do the product as in the commutator. And so this is it for Lie algebra. So everything that I'm going to talk about regarding compatible Lie algebras has an analog in regular Lie algebras, and hopefully you'll recognize some things. I will hopefully remember to bring up when things are slightly different, but at least for the beginning of the talk, this will be quite close to a Lie algebra. But what does compatible mean in my case? So the compatible adjective on the name compatible Lie algebras is a bit more general. It is a notion for algebras many other types of algebras, and what it expresses is that you can picture the following. You have two algebras over the same space of the same type. What I mean by this is quite informal, but I mean two Lie algebra structures or two associative structures or Leibniz structures and some others. And you can ask, well, I have two products of the same type defined on the same vector space. So I can ask if a particular linear combination of these maps is also a product of the same type. For instance, two Lie products, their sum, or 3 times the first one minus 2 times the second one. This might be a Lie product as well. It might satisfy the Jacobi identity, and it might not. So the question or the definition is, two products are compatible if any linear combination of them is of the same type that we started with. So formally, I written it here, but I want you to think of the words that I'm saying more than the formula here. So what I mean is two products are compatible if all their linear combinations are of the same type. And well, of course, I'm particularizing to the Lie algebra setting. So I'm going to work with two Lie products on the same vector space, where any linear combination of them is still a Lie product. Well, this is quite a complicated requirement, right? So I'll start out by telling you some very nice proposition regarding compatible Lie algebras. So two products are compatible. What I just described is actually equivalent to something much, much simpler. And this is particularly nice. I want this in black. This is particularly nice. Oh, what is happening here? I cannot change the color. Well, it will be in blue then. Well, a particularly nice property is that two products are compatible in that sense if just, oh, and by the way, I'm introducing notation here. I'm sorry if I forget to mention things, but this double bracket with the coefficients, I mean this linear combination here. So all linear combinations are Lie products if and only if this single one, this particular one, when I take the coefficients to be 1, is also a Lie product. So of course the implication 1 to 2 is obvious, right? This is one linear combination, but it just so happens that whenever I have that the sum is a Lie product, then all linear combinations are. So this reduces the problem in a very, very good way. So for checking that two products are compatible, I don't need now to check all linear combinations. We can check just this particular one. And as I mentioned, I like identities. So this is also equivalent to us having a follow, like for us to have this identity, which is just, well, the Jacobi identity, the regular Jacobi identity, but with the two products. And now I'm taking advantage of the fact that I'm not in an actual blackboard and I can just copy things, move them over. So, of course, or maybe it's not that trivial, but it's quite simple to see that two linear combinations or a linear combination of two products will always be symmetric and bilinear as well. So we only need to check something similar to the Jacobi identity. And it just so happens that, yes, we do have a mixed identity involving the same terms as the Jacobi identity, except we use the two products alternating. So YXZ, it's a bit harder than I imagined to talk while writing. Why? But there's an additional thing. So we actually, the role of the products has to be, for this to work, we don't know which product is more important, which one comes first. So actually you need to sum all the terms twice, one with the right, with the square bracket outside and one with the square bracket inside. So something like this. And so this is what we call the mixed Jacobi identity. This identity is satisfied. And we call it mixed Jacobi. And so what this means is that in practice, we can go one step further, and instead of just checking this product to be a Lie product, we can even go further and just verify, for instance, that this identity is satisfied. And so, first things first. So I told you about the concept of a new algebraic structure. Well, the first thing to ask ourselves, it should be, well, do these structures exist? I mean, are there compatible algebras? So I'm going to show you a couple. The first thing is quite trivial. So if you take just any Lie algebra that you want, and if you take the second product to be just a multiple scalar of the first one, this is quite trivially a compatible algebra. Because, for instance, this condition 2 is verified because the sum of the products is again another scalar multiple of the first, which is, of course, a Lie product. So we have a slightly less trivial example. For instance, we can take, so if you know Lie algebras, or if you like Lie algebras, you know that this is a way, this is a Heisenberg Lie algebra here, and this is an SL2. And if you put them together in this way, so I'm not going to do the full computation because it's not, well, I don't waste a lot of time, but in the PDF that you hopefully will get access to, I will write out explicitly the mixed Jacobi identity and how it is satisfied. But this is a compatible pair of products. Oops, compatible. Of course, feel free to interrupt me. I know I tend to go either quite fast or quite confusingly. So if anyone, for some reason, I mean, for a reason that I'm going quite fast or quite confusingly, if you don't understand something, just please interrupt me and I'll explain it right away instead of waiting for the end, because then it might be a bit tougher. Anyway, so these exist. So let's study them a bit. So the first thing that came to mind, and by the way, historically, as in the last 15 years or so, compatible algebras have been studied from the geometrical viewpoint, more or less. The thing is, I'm an algebraist, so we are starting to study this in a more algebraic setting, and there are some very, very basic definitions that we needed to introduce, because they weren't introduced already. So some of these are already on the literature, but maybe a couple are not. But these are quite obvious for an algebraist to think of. So from our algebraic structures, we want a few things. One of them is the concept of homomorphisms, which is quite simply in the whole of algebra, preserving a map that preserves structure, right? That's the concept of homomorphism in general. And so in our case, it has to be a linear map because we have vector spaces and we have some products. We are dealing with algebra, so we want homomorphisms to preserve products in this sense. So if you apply the homomorphism to this product, you can just reverse things and do the product of phi of x and phi of y, and the same for the second product. Well, it turns out that this notion already exists, right? If you think about it, I'm asking to preserve two products which are Lie products, so I can translate this into, well, nothing, okay, into the following. So homomorphism of compatible algebras is just a map that happens to be a algebra between the first pair of Lie brackets and the second pair of Lie brackets. I didn't mention it explicitly, but this notation I'm to denote the, so I'm going up a bit, I'm sorry, I forgot, this is very important. When I say G, I mean the vector space or the compatible algebra. So when I want to mention just one Lie algebra or the other, depending on the product, I will use this notation. Okay, for the square brackets, I'll put just a line under the letter G, and for the second product, which is the curly brackets, I'll put a tilde beneath it. So this is what it means. A Lie algebra homomorphism is just a map that is a homomorphism of Lie algebras for the first and the second pair. So the second most important thing, in my opinion, is the notion of center, right? And the center of a Lie algebra, of a compatible algebra, is, as is usual in algebra, the set of elements that kill all other elements when we apply products. So as you can see here, I'm defining the center of a compatible Lie algebra as being all the elements that, as I said, just kill all others using one product or the other. Again, I can translate this in Lie algebra terms. Quite simply, the center of a compatible Lie algebra G is just the elements that are simultaneously in the center of the first structure, so that satisfies this here. And, of course, also on the second center. So this is a quite easy characterization of center of compatible Lie algebra. And, well, this is working great, right? We have very easy definitions. Let's keep going. I think another very, very, very important thing in algebra is the notion of substructures and ideals, so in this case subalgebras and ideals. And the definition is what you would expect. So vectors, subspaces that are closed for both of the products. So they are subalgebras of both structures, and ideals are sets or subspaces that absorb all other elements when using products. And it turns out these notions are well behaved in a sense that we have everything we want in terms of ideals and subalgebras. So I'll not read all of this, but basically kernels are ideals, we can do quotients, the usual isomorphism theorems as written for Lie algebras can be just put here and they work for compatible Lie algebras. So everything is going great so far. Now, the final piece of the puzzle and the final definition for this introduction is the notion of representation. So if I want to talk to you about representations of compatible Lie algebras, I should define them, right? So a representation of a compatible Lie algebra is basically just a vector space with two representations, one for each product, right? But this time I do have to impose a third condition, a kind of compatibility of these representations, which is that the sum of representations as maps is also a representation of the sum of the products, as I have defined before. This is because a pair of representations is not always a compatible pair of representations. So before everything worked fine and I didn't need to invoke any compatibility, but here I do. And besides, you've seen by now that I like identities. So this third property of the definition, or this third portion of the definition, can be translated into an identity which is quite similar to the mixed Jacobi identity, in that I'm mixing the identity that defines representation, so the commutator identity, with both products and both representations. So I hope this wasn't too confusing. I'm just going to write it out and it should be easier. So if I mix it, if I put the wrong product inside, and I do it twice, so once like this and once like this, this is also equal to the commutator of the following. So again, mixing kind of the two representations. Either right, this product is a commutator of endomorphisms. Okay, oops, this is a and this is a y. So in practice, again, we can verify that things are representations using identities, which is good, and it's good for trying to put these things into a computer. And yeah, so let's do one concrete example just so we understand what this means. So the adjoint representation, now I have two, right? Because I have two products. It's just the fall. It's pretty standard, right? I think the only novel part is the bar and the tilde, but you can guess what everything means here. And the thing is that this is a compatible representation, because this identity here actually turns out to be equivalent to the mixed Jacobi identity between the products. So we still have an adjoint representation, and it should play a key role. And it does in some topics that I'm not covering here, which is a shame, but it works very well. So the adjoint representation is still a thing. There are representations, so let's start studying them then. So up until now, everything was working quite well, right? When we started studying this from an algebraic perspective, so representations, for instance, we were quite hopeful that everything was going to work great, but, well, life isn't that simple. And the first major thing that we tried, so I'll explain in a bit if you don't remember what Weyl's theorem is, but Weyl's theorem is very important and very central in algebra theory. And it happens that it is not true in the compatible case, okay? So to even start enunciating Weyl's theorem, I need to give you some definitions. I know this is a lot, but these are things that are well known, right? These are exactly the same again for the algebras and compatible algebras. So we have the notion of subrepresentation, which is a subspace, a representation where you can restrict the maps. And then the notion of irreducibility, decomposable and indecomposable representation, and completely reducible. So these are, even the words themselves, they suggest what these are. The only thing that I might expand on is the notion of completely reducible, because this will play a key role on the theorem. So basically, a representation is completely reducible if it can be decomposed as a direct sum of irreducible representations, including trivial direct sums, in the sense that irreducible representations are themselves irreducible. They are already decomposed. And so Weyl's theorem means, and from now on I will use the field, I'll be working over the complex numbers. It's not strictly needed, but it's easier, and easier that I mention it now instead of forgetting it later. So now, from now on, we are working over the complex numbers. And Weyl's theorem states that for simple Lie algebras, that is, Lie algebras with no ideals, all finite dimensional representations are completely reducible. This is, again, I cannot express how important this is for representation theory. So when you are studying representations of simple Lie algebras, you really only need to study irreducible representations, because all others, you can view them as like stacking Lego bricks, where the Lego bricks are the irreducible representations. So this is basically why every Lie algebra textbook has a chapter on irreducible representations, and why we study SL2 so much, and the representations of SL2, the finite dimensional at least, we just study the reducibles and let everything else go from there. And so, question, and you already know the answer because I've told you, is this true? True for compatible algebras. And yeah, it's not true, right? In fact, it's so not true that it fails at the first possible opportunity. So I will tell you about this algebra here, which has a basis x, y, and the products are as follows. X times y is x, and the other one is y. This name will be explained shortly, right? But this is one compatible algebra. It is simple. and it immediately fails Weyl's theorem. This is of dimension 2, it's the smallest simple compatible algebra, and it fails Weyl's theorem, but it fails it in an interesting way, okay? So I will tell you just very quickly how can something fail Weyl's theorem. So here we can see both the definition and the theorem. So for a representation to fail Weyl's theorem, it has to be it has to have a subrepresentation, right? Because as I just said, if it's irreducible, it is completely reducible, right? So it has to have a subrepresentation. So we need V with a subrepresentation W, but in a way that V cannot be expressed as a direct sum of W and another representation. So hopefully this made sense, and now I will show you the representation, and it will satisfy this that I just said. Well, this is it. Isn't it pretty? Right. This is a bit of a joke. I just gave you some matrices. It is true that this is a counterexample to Weyl's theorem, but I will show you with some pictures, because I'm a very visual learner, and even if you aren't, I think pictures help a little bit, and especially if I just drop you some matrices and say this is a counterexample, this is a very bad way of convincing you that this is important. So I will draw this representation, okay? And then it will be quite evident or quite apparent that this indeed fails Weyl's theorem, okay? So how do we draw a picture with related to a representation? And by the way, this is how I started to really like representation theory and algebras. It was in my master's course in representation theory. We learned about the XL to reducible representations, and Samuel, my current PhD advisor and the author of that subject, showed us the pictures and explained us the pictures, and those are, I mean, quite nice in my opinion. So I'll choose a basis for this vector space C2. I'll choose the standard basis, so it's simpler. And then I will draw a graph whose vertices are my chosen basis, start with E0. And the edges are what the representation is doing on this basis. So what does this mean? I've color-coded the maps already, so it's easier. For instance, what does rho of x do to V0 here? Well, it sends it to 0, so I could write something like this, but I'll even simplify a bit further and say that whenever I do not write an arrow, it means that the action is acting by killing the vector. And in the second component, it sends it to the first, so V1 goes to V0 with coefficient 1. Okay. Coefficients aren't important to see that this is a counterexample, but they will be important later. And I'll just continue. So the rho of y just acts here diagonally with -1, and the second component is 0, right? The red one is the same, but coefficient 1. And finally, the orange one is, well, same as the blue one, right? So I can just draw it here. 1 here. And, well, hopefully now it's a bit easier to visualize. So what is a subrepresentation in the drawing? A subrepresentation is a subgraph that whenever I follow arrows from that subgraph, I never leave. So this here, the set generated by V0, I think this is wrong. This should be 0, 1, 1, 0. Sorry, I will correct this. But the subspace here, whenever I do, I follow arrows. So whenever I apply maps from the representation, I stay here, or I go to 0, which is in the subspace generated by this. This is all fine. And now you can see how this fails, right? Whenever I try to find a complement here, so this W prime, whenever I try to find a W prime, it has to be of dimension 1, right? So because we need to sum 1 plus 1 to arrive to 2. which is the dimension of the big one. So it is basically linear combinations, or rather scalar multiples of some vector involving v1 and v0, right? It cannot involve only v0 because this is here already. But notice that whenever I apply, for instance, rho of x, that is the blue arrow, I arrive in W again. So I cannot have this piece of representation because it doesn't do what I just want it to, which is to stay there in the same place, to restrict the map and to be able to stay in the same subspace. So what happens is that I'm leaving and I'm going to W again. So in essence, this is a counterexample to Weyl's theorem, and a quite simple one. We can extend this, by the way, to a chain that is just the same thing over and over again. So the sub-representations here, they are subspaces to the left of some line cutting the drawing, and to the right, I can never have a sub-representation because I can follow blue arrows or orange arrows and arrive to the left again. So this is a very big family of counterexamples, all with the same underlying compatible algebra. But even though Weyl's theorem fails, of course, studying irreducible representations is quite important. So starting the study of two-dimensional compatible algebras and their representations, I will start by doing by studying the irreducible representations still. I will now explain a bit where the name CL24 comes from, and I'll start by classifying these two-dimensional compatible algebras. So, as a quick aside, if you know even the very basics of Lie algebras, you know that the two-dimensional Lie algebras, we have just two up to isomorphism. We have the abelian one, which is when all products are zero. So whenever you have two elements and you do a product, it's zero. And whenever it's non-abelian, you can write it, you can choose to write this product as any combination that you want, right? E1 plus lambda 2 E2, but it turns out that up to isomorphism, you can really restrict this and you end up with just one isomorphism class and you can write the product like so. In compatible algebras you have two products, so it's a bit more complicated, but there are some very easy cases. First of all, which is the abelian case. Again, it's easy, there's only one up to isomorphism because all products are zero, and then I can have one of the products be zero, and then we are exactly in the same case. So the classification starts with these three very simple compatible algebras, which are trivial compatible algebras because one of the products is zero. And so hence CL2 1, 2, 2, and 2, 3, oopsie, 2, 3. And then CL2 4 comes next. The problem is I cannot restrict this as much. What will end up happening is, yeah, so I'll write this out. I'll start from the beginning. So I can say, yeah, okay, so as before, I can have any arbitrary linear combination here, and here as well, any linear combination. I'll use a different letter. mu1, e1 plus mu2, e2. It turns out that, of course, I can play this game once and get rid of all of this, okay? So I can use the same argument and reduce the first product to this. It turns out that I can simplify it a little bit more, but not a lot more. So I can do away with one more coefficient, but I'm left with a coefficient here. And so Here, differently from regularly algebras or classically algebras, in compatible algebras we already have an infinite family in dimension 2. So this will be what I call CL24 with parameter alpha. And it turns out that each alpha gives a different isomorphism class. So this is a very neat classification in that this is it. So there's no considerations, what does alpha satisfy, what does it not. This is it. And what I called, if you are paying attention, what I called CL24 at the beginning didn't fit this scheme, right? Because the second product actually doesn't have, in this case, an X component, but this is a nicer, in my opinion, nicer way to write CL241. So this is isomorphic to when the parameter is 1. And the fact that we have a simpler description makes it a bit easier. That the first part of this representations section dedicated to this specific algebra once more, and then I'll generalize a bit. And yes, so I'll start by drawing the adjoint action for this compatible algebra, because it gave us the idea, and I'm also trying to walk you through a little bit of how this went down, not just the results, but also how they came about. And hopefully this makes a bit more sense. Again, I'll color code this here. This will be in blue, this will be in red, and this will be in orange, right? So again, now the basis, so the adjoint representation has as a vector space the algebra itself. So the basis now, so the vertices of the graph are x and y. And well, I can play the game again. Add x of x is 0, so I'm not drawing an arrow here. Add x of y is x times y, which is x with coefficient 1 here. The blue one will be something like this. Hopefully I'm not messing up any signs. So y times x is minus x times y. Here, I'm sorry. Here, x, xx, well, it's nothing again. So xy is y, so coefficient 1 here. And now the final arrow will be something like this with minus 1, I think. Well, so why did I draw the picture? Now, I can hopefully convince you again that now this is reducible. How so? Well, imagine that I have a sub-representation. It has to be of dimension 1, right? And so I take any linear combination of x and y, but then I can escape that subspace by applying, for instance, row of x, or rather the adjoint of x here. So yeah, I'll write it down, sorry, I have a tendency to, so row of x of, I don't know, any linear combination, lambda x plus lambda y. Well, it kills x, and to y it simply keeps the coefficient and gets it to x. So, well, right away with any vector space, vector subspace, I can escape it. So there's no subspace, that is a representation, so this is irreducible. And so the question is, can we keep going? Can we extend this in the same sense that we did for the counterexample to Weyl theorem representations? So what do I mean by this? I mean doing this in a line. And so yes, this is what we call a finite dimensional irreducible line representation, because it has the shape of a line. And one very important thing here is I'm not claiming that these are the only irreducible representations, okay? We don't know yet if they are, but this is a good attempt and a good start, because if we have the orange and the blue arrows always there, so if the coefficients are never 0, this is irreducible by the same argument I just used here. We just iterate the argument, and we cannot have any vector or any subrepresentation. So what's happening here? This is very, very general. I have all the coefficients free. But for this to be a representation, there are some constraints. And so our question was, well, can we classify all of these? And the thing is, we have a lot of constraints, actually. What happens is that betas have to go up, so whatever this is, the next one has to be that plus 1, and so on. The gammas are also constrained in the same way. They interact with one another. Well, all sorts of restrictions. And if we count the restrictions and the free parameters, we end up with just one actually free parameter. I'm cheating a bit here, so alpha and delta, so the orange and the blue arrows, they are constrained, but only the product, so I could change one as long as I change the other. But up to isomorphism, this changes nothing, because this is the same as scaling one of the basis vectors. So in essence, I have only one free parameter. And besides, so this is what really jumped to our attention. So we were starting this study, well, I don't know, trying to see something interesting happen, and this was the point where I think something very, very interesting happened. So I will, so this is a drawing now with the constraints, right? And some of you may know what's coming now. If you remember, or if you are familiar with the representations of SL2, this kind of looks the same. What do I mean? The representations of SL2, the finite dimensional ones, that are the building blocks, they look like this. So we have EF and H acts diagonally, E and F go up and down, and it happens that the coefficients of this, what by the way I'm going to call the n beta 0 because of the parameter, the coefficients of these turn out to be the same coefficients as the SL2 ones. Well, up to a minus sign here on the orange arrows, and the diagonal action isn't explicitly here, but if we sum the diagonal actions on each vertex, we have exactly these coefficients. So what I mean by this is beta 0 plus minus n minus beta 0 is exactly this minus n. The next one, we have a 2 left over, 1 plus 1, so minus n plus 2, and so on. So intriguingly and surprisingly, the small simple compatible algebra, at least one of them, its representations are very, very similar to the representations of the smallest simple classical algebra. So this is what piqued our interest first. Now I'll just redraw this with the following coefficients here, just for ease of computations later. Basically, I'm just putting all the blue arrows to 1, and the orange arrows have the product of the coefficients. This is isomorphic, this is just changing the basis vectors. But I'll do this from now on. So, our thought now was to try and find either irreducible representations that did not have the shape of a line, or find some more counterexamples to Weyl's theorem. So representations which have subrepresentations but they are not decomposable. And one thought that occurred to us was to try and do tensor products, because in a second when I draw it, you see how the shape changes, and so if that's irreducible, great, we have a different shape of irreducible representation. If not, well, we can try to find a subrepresentation with no complement. And so the tensor product of representations is exactly the same as for the algebras, except we have 2, right? But they are what we expect. The first one is a product of the first representation here, and the second as well, and it turns out that we don't need to impose anything else, and this is a compatible representation for free. So that's great. Well, I'm going to do an example now. So with those line representations, we try to write them down and see what happens. So I will start drawing and talking about this one here. If you draw a graph like I drew for the line representation, you can see that this graph will be a rectangle. It will be kind of like the Cartesian product of the Cartesian product of the other two drawings. And notice that I'm drawing very, very few arrows, because the orange ones, so the ones that go in the other direction, so it will be something like this here. Well, there's one for each blue arrow, and the coefficients can be determined, so I'm not going to write them. And for the diagonal actions, if you work it out, I'm just going to write it, not work it out explicitly, but it turns out that this here, for instance, the red diagonal action and the light blue one goes in the other direction, but this has value 0 here, value 1, so that means eigenspaces are kind of these diagonals on the drawing, right? And so the question here was, first of all, trying to find a sub-representation. So we did the most obvious thing, so I'll start with a fresh drawing here. We did the most obvious thing, which is, well, if we start here, I have an element, right? One, so in this case, this will be V4 tensor product V3. So the V4 from the first one and the V3 from the second one. I'll write this as W43 as to make it simpler. And I can start with this, calling it D7, and it will be apparent why in just a second. But if I apply rho of X, I end up with a linear combination of these here. In this case, it will be just, let me count, 1, 2, 3, 3. So W3, 3 plus W4, 2, hopefully. Yeah, and I can keep going, just one more so I can tell you about how binomial coefficients appear, which is quite neat. So you may know that one of the ways to count, or rather one of the ways to express binomial coefficients is the number of paths in a grid, so they appear here. So this element here on the following iteration, it will have coefficient 2. It will be 1 times that one, plus 2, plus 1, and so on. So the thing is, why is this helpful? Well, this obviously works well for the row of X by definition. The diagonal actions, as I said, the eigenspaces are the diagonals in the drawing, so this works well for rho of Y and for mu of X. And the only thing we need to check would be the orange arrows, right? So the ones going in the other direction. We were lucky in that, yes, it works. So this is not obvious at all. We had to work it out, but it works. And so this is a sub-representation. So great. By the way, if I keep going, you can see that this is a line, right? D3. And so if you count, this is isomorphic to write it as 4 plus 3, so it's even clearer where this comes from. So it's a line representation whose size is the sum of the sizes of the ones we started with. So this is a great point to think what might happen next. We had two options: either this is a counterexample to Weyl's theorem, and so there's no complement, or it is not, and there is a complement. So we started to, first of all, trying to work out what could be such a complement. I'll put this like this. It turns out that if you count what we removed, so if we want something like V is the direct sum C, if we count the dimension that we removed, we end up with something of this size here. So an attempt at another subrepresentation that could be a complement is some subrepresentation which has dimension 3 times 4 in this case. One way, and a very visual way to do that, was to try and okay, this will be, hopefully this won't be too dumb and too weird, but we put dots here and so on. But what do the dots in the drawing mean? Well, for us it meant a linear combination, something like, so this was W 0 1 plus W 1 0, and if we were lucky enough, hopefully we could do this for all these dots here in a way that we could determine the coefficients and make it work. Were we that lucky? Well, let's see. So all the dots are here, that's what I meant, and it turns out that from the way we did things, well, this is not working properly. It appeared now. So from the way we did things, the blue arrows do work. Again, luckily or by virtue of our great choice, the diagonal actions here, if you focus on just the green dots here and here, they seem to work in the same sense. So in the same sense, I mean, this seems to look like this here above on a smaller scale. And so we just had to verify, and the word just is lifting a lot of weight here. It was a bit tough, but we had to verify that the one that was left, again, mu of y, the algebra worked, and it did. Basically, we found that this I should have organized this a bit better here. I'm sorry, let me just pull this down a little bit. If I'm calling this, that's in between C01 and W01 and W10, this will be C00, so 0, 0, and then Cartesian coordinates again, 1, 0, 2, 0. Well, all these vectors here, provided we choose the coefficients well, and I'm not explaining how, but we did manage to find another subrepresentation. And moreover, it turns out that this is a subrepresentation with the shape of a smaller tensor product. And it turns out that, yes, it is a complement to our line representation here. So, and now this was the point where my slight lack of experience as a PhD student showed. And after all of this, when I was about to start working on this C representation, Samuel, one of my advisors, told me, "Oh, that starts to look like the Clebsch-Gordan formulas." And I'm like, "Okay, let's explain that to me, please." And he did, and I looked it up further. And it turns out that we have exactly the Clebsch-Gordan formulas for SL2 in this algebra and in these representations. So what started as a coincidence, as well, these representations here, they look like SL2 representations, they keep looking even more like SL2 representations in that the tensor products satisfy the same Clebsch-Gordan formulas. Well, I told you I was going to talk about the general case now. It's a bit disappointing. I hope you don't get as disappointed as... Well, let's see. What happens is we did find a family of line representations for these algebras here, the general case. And here is an example, right? So this is generalizable in 4 dimensions. The coefficients would be, or in 5 dimensions, the coefficients would be -4, -3, so on. So this is a family as well. But there are a few problems. Okay, so when I sent the abstract, or when I got invited to give this talk, I was very hopeful that we would have some real results here. But what happens is we don't know if this family is the only one of this shape up to isomorphism in the same sense that the previous family was. Besides, you can see that there are a lot more arrows here. So this is way more difficult to work with. And thirdly, we don't know exactly if there are counterexamples to Weyl's theorem here. So just a piece of the drawing, a counterexample to Weyl's theorem would be something with all the arrows pointing in the same direction. And that's what I mean, because with the same argument, we could just separate the drawing here. And so we found a family, which is great. So this is always irreducible, but that's it. Everything else. So this is our problem. So the questions here are: is there a classification? Yes or no? We don't know. How do tensor products behave? Well, the previous drawing here was already painful enough. With all these actions here, I'm not so sure we can do it by hand, and I'm not so sure I can program a computer to do it as well. So we don't know if there's Clebsch-Gordan formulas for the other algebras of the family, and if there are counterexamples to Weyl. This one here, I think, is the next one to tackle. We think there are. It should be a bit easier, but these first 2 questions seem to be a bit hard. And I had one more section, but I don't know if you noticed on the first page of the slides, I had it in between parentheses because I knew I would probably not get time. So I'll just very quickly tell you that some other very important theorems fail. But they still fail in interesting ways. So the fact that semisimple Lie algebras are direct sums of simple ideals is not true for compatible Lie algebras, and the counterexample is also based on this CL24, and Levy's theorem also fails, and the counterexample, you guessed it, is based on CL24 as well. I will leave this in the PDF that I'll send Ivan to publish on the page, so you can look at it if you'd like, even though I didn't have time to explain. And so this is it for me. Thank you all for coming. Thank you, Ivan, for inviting me, and I'm done now. Thank you very much. We did start 2 or 3 minutes late, so I guess there's 2 or 3 minutes for questions if anyone has them. Well, I think I'm sharing for myself here, I don't know. So, Michael, I suppose you can, well, ask whatever you want.
Okay, thank you. Thank you for the very nice talk, Bernardo. I wasn't able to see, because it was right at the end there, your definition of semi-simple for compatible Lie algebra structures. Does that imply that each of your 2 Lie algebra structures are themselves semi-simple?
Yeah, I know there was no time to talk about this definition. I'll try to be very brief, but we can have a notion of commutator of subalgebras, which is the same. And then all definitions stemming from that, so nilpotency, solvability, all that, the definitions are the same. Means that there's this series which stabilizes or reaches 0 or doesn't. And in particular, this definition is a bit stronger than each of them is solvable. So, sorry, I hesitated a bit. A compatible Lie algebra, if it is solvable, then each component is solvable as well. but we can
Okay.
have Lie
I was
algebras that.
actually asking about the semi-simple case there.
Oh,
So
sorry.
if
Well,
it is semi-simple, does it mean that each of the two Lie algebra structures is semi-simple?
also no. So it's semi-simple if it doesn't have a radical. So all of this propagates a bit. So the definitions are a bit. They are natural in the algebraic sense, in that we have a series of derived series, and the radical is the unique maximal solvable ideal, and it's semi-simple if it doesn't have a radical. The truth is that for semi-simples, we haven't really figured out a lot. For nilpotent, for instance, it works quite well. For semi-simple and solvables, well, clearly it doesn't, because Levi's theorem fails, so it doesn't work very, very well, but there's something here, surely. And in particular, yeah, so there are semi-simple compatible Lie algebras where each component is not itself semi-simple. So
Okay.
semi-simple as a Lie algebra. So I talked a lot, but the answer is yes. So this CL24 in particular, it is simple. So let me see the first definition I had of it. Yeah, it can be here. So this here, of course, if you ignore one of the products, this is not simple nor semi-simple. It's the two-dimensional Lie algebras, they behave badly, but together this is simple, and in particular semi-simple.
Yes. So I was wondering if the condition of each of the Lie algebra structures being semi-simple was what was needed for complete reducibility of the finite dimensional modules.
That's a great question. Let me. So the answer is I have no idea, but this is a good thing about giving talks, is that people ask very obvious and very important questions that I hadn't asked myself yet. So I will write it down in my notebook, and hopefully next talk I give, if you attend, I might have an answer. Who knows? So semi-simple components. Well, thank you very much for your question, which unfortunately I have no answer for.
Okay, well, thank you very much for the talk.
I would have a question. Do you have a similar notion at the group level? Do you have a notion of the two compatible Lie group structures on the same?
So that question is very interesting. Unfortunately, I know very little geometry. I know very little about Lie groups. I've asked myself that. I've been asked that, and I don't know. As I started wanting to know, and in my PhD, so I'm in my fourth year. So in my first year, I was thinking a bit about that, but then the algebra side took over, and then I started studying algebraic questions. But hopefully myself later, or someone else, can come along and give an answer to that, because if there is a notion of compatible Lie group, it looks different, because there's no sums in compatible Lie groups, so we cannot do linear combinations of the products of a group. So, but if there's something, it looks different, and different is interesting in my opinion. So that would be a very great thing to have, a compatible notion at the group level. But unfortunately, I did not go in that direction.
But I think you could push even your example with these two-dimensional structures. You could integrate them, so you have kind of two copies of the H plus B group, but and they should be compatible in some sense. I think you could push this example for.
Okay, I will think about that. I will probably try to find a geometer friend who is interested in this, because truly, I really think that's an interesting question. I'm not saying this as you do always. I really do think it's interesting, but I don't know enough geometry. Even I don't remember enough of my manifolds course to do that alone. But if I find some help, I would like to actually to explore that. Well, I'm not sure. I'm sensing that the silence means no one else has any questions. So I assume we are done for the day. I don't know. It's very weird sharing for myself. I don't know if whoever was going to be the chair just forgot or isn't here. But in any case, if there's no more questions, thank you very much for attending my talk. And
by the way.
thank you very much. And so see you all next week at the seminar. And thank you very much once again.
Bye.
Bye.